Welcome. And we are going to be talking about, as you probably are guessing, radiation and spectra. Let me put this right here. Better. Radiation and spectra. Let me see if I can advance slides. I can. Awesome. I hope that you all are seeing what I'm seeing. Anyway, so one of the most challenging things, and in my opinion, one of the most impressive things about astronomy is that this is a made up number, but it's close. I would say that about 90 to 95% of all of the information that we've gained in astronomy, the information that I'm going to be imparting to you in this class, has been derived from the observations of light. It's not as if at this point we can actually stick Jupiter in a lab and manipulate it and figure out its composition in that way. The only way that we can find out very fundamental things about objects, such as their mass or their radii, how hot they are, it comes from the collection and analysis of light. And so it is vital, I think, for me to start off, or at least talk about light before I talk about any of the physics or any of the astronomy that has come afterward from it. So, um, features of light. I talked about gravity and all that sort of thing last time, but light is also one of these concepts in physics that is actually kind of not well known. Certain aspects of light are very well known, but if you want to get into the nitty-gritty of what is light, what is it physically, we don't know. We can describe light very well, exceedingly well in some location or some situations. But what light physically actually is really open to debate. Um, for myself, when I conceptualize light, for me, light is simply the communication of information or energy from point A to point B. The reason why we know or one of the ways that we know that things are happening around us is because light is emanating from that event, traveling through space, air, or whatever medium, and then hitting our eyes and being recorded and interpreted by our brain. So for me, that exactly what is life. But the best that we can do now is try to figure out describe it in some way. Back in the back in the Newton times, around the 1600s or so, when the first experiments of light were being done, Isaac Newton was one of the first pioneers of a field of astronomy or field of physics known as spectroscopy, where what he noticed was he took sunlight and he passed it through a small slit in a wooden screen, and it basically created a beam of light. He then shot that beam of light through a piece of glass, and what he noticed was on the other side is the familiar prism effect of the rainbow pattern of colors. And so he recognized that white light from the sun, for example, is actually composed of all the different colors of the rainbow, literally. And then further studies have expanded it outward. When Newton thought about light, he actually thought of light as being, the term is corpuscles. I can't remember, I think he actually used that particular term, but you can think of it as packets of light, small bits of energy traveling through space. But very quickly, there was a dude by the name of Huygens who didn't really get along with Newton, to be honest with you. Uh, and another gentleman later, young Thomas Young, both of them actually did experiments where the only way to describe, or the only way it made sense for the observations the only way that the observations could make sense is if light was actually a wave, kind of like a wave going through water. And so now, and then around the turn of the 20th century, dude by the name of Niels Bohr basically, and Max Planck, they basically realized that, well, actually, you can also think of light as a particle because they came up with experiments that could the best way to describe them or the best way to interpret the information or the result was to think of light as a particle or a corpuscle. That is where we get the term photon. A photon is just a little bit of light that is carrying, or a little bit of energy. So it's light carrying a little bit of energy as it moves forward. And depending on the situation, we use those two terms, or we use those two ways of looking at light effectively interchangeably. In some ways, it is much easier to analyze light as if it's a wave. In other ways, it is much easier to interpret it as a photon. For the most part, I am going to be use language that I'm going to be using wave-like language. I'm going to be imagining and describing light as a wave. But in certain circumstances, I am going to think of it as a photon. Even later in this class, I will be looking at it as a photon. And then when we talk about detection instruments, how we actually collect the light, it is easier to think of light as a photon as opposed to a wave. So, waves. You have two kinds of waves that travel through. Oh, real quick, I'm not going to try to do poll everywhere online, so I'm not going to be asking questions through this, for better or for worse. So if you're anticipating a question, don't worry, I'm not going to be asking any during this particular lecture. So, waves. There are two types of waves. There are compression waves and then there are shear waves, or more specifically, there are what we call longitudinal waves, which is a compression wave, and a transverse wave, which is a shear wave. Um, Sound is a compression wave. Light can be thought of as a transverse wave. Water is like a transverse wave. And the main difference between the two of them is, imagine you have a bit of matter or a bit of bit of matter on the wave and the spring or the ribbon. When you move the spring, the bit of matter will travel left to right. It will travel in the direction of propagation. So as the wave moves forward, if the spring is attached to a wall, as the wave moves towards the wall, any bit of piece of material on that spring is going to move toward and away along that line or along that area. With a transverse wave, if it's on a string, then when you propagate the wave, again, the wave is going to propagate towards the wall. The bit of matter is going to just simply go up and down. It actually goes perpendicular to the travel of the wave. Now, um, we will be coming back to compression waves again because we are talking about light. Light is a transverse wave. That's pretty much, you're going to see that a lot. But we are going to come back to the concept of compression waves when we start talking about seismic activity and talking about how we have determined, at least roughly speaking, the composition of the Earth, or how the Earth's structure is below the crust. So, a couple of properties to note. First two are wavelength and amplitude. And I'll start off with amplitude because that's we're really not going to get back to that in this class. It is amplitude is really um, the intensity. You can think of it as the intensity of light. You know, the larger the amplitude of the wave, the more light you are actually receiving, or the brighter the light that you're actually receiving. It's analogous. But wavelength is important. Wavelength is the proxy for the size of the wave. And so wavelength determines essentially the length of the wave from where it starts and then where it basically returns to that same point as the wave propagates through. So, for example, the wavelength, if with this diagram, the wavelength can be defined as the distance between the peaks, or you can do it as the distance between the troughs. So long as you're comparing apples to apples, so long as you're comparing the same positions relative to each other, you can define the wavelength. Then we have something known as the velocity. A wave, as it propagates with a certain speed. Hopefully, folks have been um, recognize this. When you look at water, you can see that water waves sometimes travel very quickly through the water and sometimes not. Water, the velocity of the wave is a simple function. Sorry, I'm trying to find the person who's not muted. The Again, we get back to a fundamental property of physics is expressed in a very easy way. The velocity of light, or the velocity of a wave, is the wavelength times a quantity known as the frequency. Oops, come on, there we go. Frequency is how frequent does, say, a peak of a wave travel over a set distance, or rather over a set time. So if we look at this wave, we study this wave for a second. The frequency is how many peaks have we seen pass by us every second. Probably more familiar with, or a better or a more familiar way of looking at this is the refresh rate of a computer monitor. So nowadays, I think they're getting up to 120, 240 hertz. What that means is that for 240 hertz, your screen is updating itself 240 times every second. So that indicates the frequency at which your computer screen refreshes itself. And so again, the velocity of a wave is equal to the frequency of the wave and the wavelength of the wave. And so frequency and wavelength are inversely proportional to each other, assuming you have a set speed, which when it comes to light, that is the case. So again, V equals F lambda. Light, as we as we'll see, travels, and basically the as Einstein would Einstein has stated in his special relativity, light has a maximum speed through of which it can travel, and that is c, and that is approximately 3 times 10 to the eighth meters per second. Information, according to relativity, light and information, or rather information, cannot be transmitted any faster than that speed. It can travel slower, but it cannot travel faster. That is the ultimate universal speed limit. In fact, if you put light in any other sort of medium, even air, what you'll find is that the velocity of light is actually slower. Not much when it comes to air, but in water, it's actually pretty slow. And there's an entire field of study of physics whose ultimate goal, the holy grail, is actually to get light to stop, is to develop a medium where photons that are that enter the medium just basically hang out right there, kind of like a Kylo Ren situation in Force Awakens, where we can actually freeze light in its path. We've come close, but as far as I'm aware, we haven't actually gotten there yet. So When we look at light, the equation now becomes C, a constant, is equal to frequency times wavelength. So now they are frequency and wavelength are directly proportional. If you lengthen the wave of light, then its frequency drops down. And when you look at light as a function of either frequency or wavelength over all possible frequencies and wavelengths, and at this point, there is the expectation is that that range is infinite, that you can have an infinitely long and an infinitely short wavelength. When you look at that whole thing, that is known as the electromagnetic spectrum. Now, for reasons that I'll get into in a moment, we have decided that astronomers and physicists have decided to split the electromagnetic spectrum into certain regions, going from the longest wavelengths to the shortest wavelengths, or rather the highest frequencies, I'm sorry, the lowest frequencies to the highest frequencies. You have radio, and in radio, you also have microwaves and Wi-Fi and TV and so forth. Getting to shorter wavelengths, you have infrared, then you get into the visible, then ultraviolet, then X-rays, and then gamma rays, finally. The boundaries of these regions is somewhat arbitrary, except for visible light. Visible light is biologically determined. Um, let's see, what did I skip? Yeah, different kinds of light. Visible light is biologically determined. It is essentially the average limit of human vision. So visible light is defined as the region of the electromagnetic spectrum between around 700 to 450 nanometers. What is a nanometer? A nanometer is 1 billionth of a meter. So take a meter, divide it into a billion equal parts. The size of one of those parts is a nanometer. So very small. The rest of the spectrum is again somewhat arbitrarily broken into certain waves. I'm actually going to do this backwards. Now, the reason why we want to split the electromagnetic spectrum into various different regions is in a way it's sort of a bookkeeping sort of idea because of yet another very simple equation, and that is the energy carried by the light is equal to Planck's constant times the frequency. Or you can rearrange it where E is equal to hc over lambda. But it's a very simple relationship. If you know the frequency or you know the wavelength of light, you know how much energy is being carried by that. And what that indicates a temperature, or does indicate a temperature of the phenomenon that created that light in the first place. So if you were to determine the light of um, so if you look at, for example, a package of a LED light you might notice that it has some number like 4000 K or 6000 K. What that indicates to you is the wavelengths of light that it puts out are equivalent to something that has the temperature of 4000 Kelvin or 6000 Kelvin. We'll return to that in a moment. But effectively, when we look at astronomy, when we look at these wavelength, or when we look at the electromagnetic spectrum, say we want to know about supernovae. We want to know what creates a supernova, what does the aftermath of a supernova look like in terms of the temperature and the physical composition and that sort of thing. Looking in the radio is not a great idea because supernovae are incredibly energetic. They are the second most energetic thing in the universe. They have a tremendous amount of energy. So most of the light is being put out in the X-rays and gamma rays. So if you want to do this kind of study, you need to have telescopes and cameras that are sensitive to X-rays and gamma rays. Radio really isn't going to cut it. Conversely, if you want to know about just normal cold hydrogen gas that is permeating through a galaxy that isn't anywhere close to a star, that gas is very cold. And because it is very cold, it's not putting out a whole lot of high energy photons. So if you wanted to map out where the hydrogen is in our galaxy, for example, and that would tell you where the stars would form, generally speaking, doing an X-ray or gamma ray survey isn't the best idea because, again, you're not going to get a lot of light in that region of the electromagnetic spectrum. Here, radio is much more appropriate. Using radio telescopes to scan the sky, you actually get a lot more data, or a lot higher signal, a lot more data in terms of observing light emitted from uh, cold hydrogen gas. Doppler effect. Now, you may be familiar with Doppler effect, particularly if you're an audiophile. Doppler effect is, generally speaking, introduced to students as a sound phenomenon, and including this graphic. So, for example, you have a no, I'm not going to make that comment. You have a police car with a siren, and you've probably experienced this yourself. When that police car is traveling towards you, you notice that the pitch of the police car's siren is high and almost shrill. When it passes you, the pitch drops significantly. And that is because of the Doppler effect. Now, let's look at this in terms of waves. Every second, for example, corresponds to those those ovals. So the first second is the number one oval, the second is the number two oval, so forth and so on. And so as the car moves and time progresses, those waves move outward at a or at a set speed described by the frequency and wavelength of the sound. If the car were stationary, then those waves would come away from the siren at the exact, or basically at the frequency and wavelength is the same for any observer that's around it. So everyone would essentially hear the same pitch from that siren. But because the car is moving, effectively the waves in front of the car become compressed, almost stacked on top of each other. And if you have a shorter wavelength and the speed is the same, again, we're traveling through air, the same medium. The sound is the velocity of the sound wave is the exact same, is held constant. If you drop drop the wavelength, the frequency goes up, and so the pitch goes up. Conversely, when you're on the other side of the car and it's moving away from you, the waves become more dispersed. They become further away from each other. The wavelength grows, the frequency then goes down, and the pitch drops. Astronomically, we refer to these two phenomena as blue shifting and red shifting. If we go back to visible light, if you want to know the color of 700 nanometers is the reddest of reds that you would be able to see. 450 nanometers is the most violet of violets that you would be able to see. So as you progress to shorter wavelengths, the color becomes bluer. Oh, thank you. Letting him in now. As the wavelengths get shorter, the light becomes bluer, and the if it's moving away from you, the light becomes redder. This becomes a this is the principal way that we can determine the velocities of something moving away or towards us. So if we wanted to know, say, how fast the Andromeda Galaxy was moving towards us or away from us, it's moving towards us, then we could look at the color of the Andromeda Galaxy and see if it's been shifted to the blue or bluer end of the spectrum or the redder end of the spectrum. Then we would anticipate if it were just stationary. All right, interacting with light. Light interacting with matter. No one in the waiting room. So light can interact with matter in four general ways. Light can be emitted from matter. Light can emanate from matter. Light can be absorbed by matter, or light can be transmitted through matter, or finally and refracted, changed its in the process the direction of the light can change, or it can be reflected. The direction is thrown out. It is now no longer traveling in anything remotely in the same direction that it was before. So, like a mirror, the light from a mirror is reflected. Or you could have light being scattered. Light hits a dust particle and then it sends the light off in some random direction. When it comes to the third thing that I mentioned of light transmitting through a substance and its direction changing, that is known as refraction. And if you're looking at multicolored light, then you get a phenomenon known as dispersion. Because blue light bends or gets refracted more than red light does. That is how you get that prism. So you start off with white light, light that has all sorts of wavelengths to it. And then when it hits glass at an angle, the blue light gets bent a lot, and then the red light gets bent slightly. And so it broadens out that light beam. And in so doing, it creates bands of different colors which correspond to light of different wavelengths. Dispersion, like for example, um, a light source in the prism. Again, this is what we this is the experiment that I mentioned with Newton. He took light from the from he took light from the sun, blocked it with a piece of wood with a slit cut into the center of it so that he could create a beam of light. That light then hit the prism, and that caused the light to bend. And then when it hit the light, hit the air again, it bends even more and creates this rainbow pattern. Incidentally, one of the anecdotes that I love telling about Newton was Newton was a little nuts, particularly later in life because inhaling mercury fumes not recommended. Um, he was really big into alchemy. One of the stories that I've heard is that when he looked at this, when he found this when he made this discovery, he was curious on what would happen if the glass were deformed in some way. If you deform the glass, then how does that beam of light change? And this is the 1600s, so it's not exactly like he can get a piece of glass or a piece of plastic and bend it. And so he came up with a different idea. He realized that there is a lens in your eyeball. So he took a little steel rod and stuck it in his eyeball and kind of was attempting to um, basically bend or manipulate the lens in his eye to see what would happen. As far as I know, nothing of real note actually came out of that experiment. But uh, it's kind of, I like it because, again, it shows that Newton was a little nuts. When we look at the dispersion of light, uh, that is that is known by another name, and that is called a spectra, or a spectrum of light. That is the dispersion of light from a whole bunch of wavelengths into individual packets of wavelengths. So from white light into a rainbow pattern of color of one variety or another, that is known as a spectrum. And there are three types of spectra. A German by the name of Kirchhoff came up with these. There is a continuous spectrum, there is an emission spectrum, and then there is an absorption spectrum. A continuous spectrum is just like I just showed you with the prism. It is a continuous band of color moving from red wavelengths to blue wavelengths. An emission spectrum looks like the one in the middle. The emission spectrum looks as if you have taken that rainbow pattern of color and removed most of it, and you're left with thin little bands, basically small little areas where the light still exists. You still see the color in those, and that is known as an emission spectrum. The absorption spectrum is the inverse of that. So instead of removing a lot of light, you have now removed only a little bit of light. You've removed those little tiny bands from the continuous spectrum. And so now you have effectively a bright band of color with dark lines running through it. And depending on the type of spectrum that you see is then dependent on what is physically happening to the light as it is being emitted from a particular light source. So imagine you have a a light source that is incredibly dense or dense and very, very hot. So the typical terrestrial example of this, which we no longer use, is an incandescent light bulb. So the light bulb that Edison uses, the way that it works is very simple. He takes a piece of tungsten, which is a dense metal, and he passes electricity through it. When that electricity tries to move through the tungsten, the tungsten has a very resists it. The tungsten resists that motion to a very high degree. And the byproduct of that is that the tungsten heats up to a very high temperature. That is what we refer to as a source of a continuous spectrum. When you have something that is very dense and very hot, the light coming off of that thing ranges the span of color from red to blue. Now let's imagine you have this cloud of gas, which can also be hot, but is not as hot as the continuous spectrum. So it's cooler and it's definitely less dense. So it's rarefied in some way or another. Now, let's say that you have the continuous spectrum to your, the light source to your left. You're looking at the gas cloud to your right, and you have a spectrograph, something that creates a spectrum. You look at the light, you look at the light source and only the light source, you see that continuous spectrum. You look at the cloud and only the cloud, you see that emission spectrum. Now let's position things so that now you are looking at the continuous source or the light bulb through the cloud itself, through the colder, less dense cloud. Then you get an absorption spectrum. This is known as these are known as the Kirchhoff laws. Kirchhoff's laws. Now let's backtrack a little bit and talk about the concept of astronomy, the field of studying of the spectrum, that is known as spectroscopy. Spectroscopy is the analysis of light as a function of wavelength or frequency or energy. And so the tools of a spectrograph or a spectroscopist are effectively some kind of dispersing device, be it just a normal prism or be it something known as a diffraction grating. They use something that takes in light from a particular source and they spread it into as fine a spectrum as they possibly can or as they need, where they can see that continue or that variation of how bright the light is as a function of color. When we zoom in on what a continuous spectrum is, we get to something known as a black body. A black body is a theoretical object in physics. A black body is something that emits all of the radiation that it absorbs, and it does so in a continuous sort of way. Basically, it creates a continuous spectrum. It puts out light continuously over all wavelengths, meaning that there are no dramatic spikes in the light and there are no dramatic dips in the light. It's a smooth curve as you go through it. That is known as a black body. A black body, the characteristics of a black body are effectively determined by one parameter or one property, and that is its temperature. So if we look at this graph, what we're seeing is wavelength along the x-axis and intensity, or you can kind of think of amplitude of the wave in the y-axis. The rainbow pattern of color indicates the visible part of the spectrum, basically the part of the light being emitted off of this object that we can see. The lines indicate how much energy is being produced at any particular wavelength by an object at the listed temperature. So if you look at the 2000 K, K standing for Kelvin, it's roughly equivalent to Celsius, you see that the line is barely off the x-axis. There's not a lot of energy, comparatively speaking, coming off of an object that is 2K. If you look at it in terms of wavelength, most of the wavelength or most of the energy is actually being emitted in the part of the spectrum we can't even see. That is the infrared part of the spectrum. So this is, you may have run into, and I highly recommend that you do this. Google an infrared image of a dog. It is really, really cool. Effectively, what you're seeing is the heat, where the heat is distributed on the dog's head. And as we all know, the nose of a dog is very cold, and so the nose is almost black, whereas the ears are very, very hot. Anyway, so if you're wanting to look at something that is cold, as I was talking about before, then you want to admit someone from the waiting room. When you're looking at something cold, it's better to look at it in the longer wavelengths because most of the energy is being put out into space at those longer wavelengths. As you increase the temperature of the object, two things happen. One, it produces more energy. Hopefully that makes sense. If something gets hotter, then it produces more energy. More photons are emitted off of the thing. Uh, it is, you don't get burned by a colder object because there's not a lot of heat coming off of it. There's not a lot of energy to burn you for. But if you heat the thing up so that it is white hot, then there's enough energy there to cause damage to your skin if you were to touch it. So that's the first thing that happens. When you make something hotter, then that object is putting out more energy. The second thing, hopefully you'll notice, is that the peak of this curve, the wavelength at which the most energy is being emitted per second, that shifts towards the blue. So the peak of a 2000 Kelvin star, for example, would be in the infrared. The peak of a 5000 Kelvin star would be basically in the yellow-green part of the spectrum. So if we're looking at the sun, for example, it is very much appropriate to look at the sun, filtered, by the way. Don't look at it without some kind of, don't stare at it. That's what I'm trying to say. When we're looking at the sun, most of the light coming off the sun is put into the visible part of the spectrum, and that is probably not an accident. Uh, I would imagine the reason why we can see in the visible part of the spectrum is because that's where most of the light the sun is putting out is. So that is why we are that that basically is the reason why the visible light spectrum is defined that way. If you look at a 10,000 Kelvin star, now most of the light is not, again, most of the light is not in the visible. It's actually in the ultraviolet. It is the instead of infrared is on the colder side of visible, ultraviolet is on the warmer side of visible. So those are the two properties of effectively a black body curve. How much energy or the area underneath that curve and the wavelength at which it spikes or the wavelength at which it peaks. So that first relationship can be known mathematically by for us to see properly, it has to be not too hot, not too cold. Effectively, yes. It has to be in order to yes, in order to see it well, or more most efficiently, then it does have to be in this sort of Goldilocks zone where most of the energy is put out with light of wavelengths between 700 and 450 nanometers. The first property that I was talking about, the hotter the thing is, the brighter it is you can mathematically describe that using something known as the Sifon-Boltzmann law. And that is that the luminosity of an object, effectively how much light is being emitted from that object every second, is equal to a constant known as, imaginatively known as the Stefan-Boltzmann constant, times the surface area of the thing emitting the energy, or the black body, times the temperature of that black body raised to the fourth power. So a what that means is that a small change in temperature actually produces a fairly dramatic change in the amount of energy that you can that is put out. And hopefully you can see that with these curves. So if you go from 2000 to 3000, you have a fairly small change in the amount of area, or you have a the smallish change in the amount of area underneath this particular curve. If you go from 2000 to 4000, you now have significantly more. You have more than doubled the area underneath that curve. You've actually quadrupled the area underneath that curve. So astronomers now have a way to determine one very fundamental property of a star, for example, its temperature. All we need to know, exactly, effectively, is two things. We need to know how bright the thing is and how big the thing is. If we know those two things, then we can get the temperature of the thing. Or conversely, if we know the temperature of the thing and we know how big it is, we now know how much energy it's putting out. And you can do the same sort of thing with the size of the radius or diameter of the star. Again, if you know two of those factors or two of those properties through some other method, you can get at the third. And that's really kind of one of the name of the game when it comes to astronomy is usually these properties are related to each other, and if you can determine what the properties, some of the properties are from some other method, then you can derive or measure or calculate the property that you want to know. That second property that I was talking about, where the wavelength gets shorter as it gets hotter, is simply known as Wien's law. Oh, I need to change that slide. Wien's law is extremely simple. Wien's law is the wavelength at which it peaks is equal to some constant divided by the temperature. So it is an inverse square law, or excuse me, it is an inverse law. You double the temperature, you have the wavelength that it peaks at. So, like I was saying before, the hotter the object is, the more into the blue, into the ultraviolet that the light, most of the energy transforms into. Is the Stefan Boltzmann equation about radiation and light? Um, that's actually a good, thank you for asking that question. The answer is yes, but when the, in sort of colloquially, when people are talking about things, they will often talk about light and they will often talk about radiation as being separate things. They're not. Light and radiation are synonymous. They are the same thing. Generally speaking, when you talk about radiation, you are specifying the light in high-end spectrum or in the high end of the electromagnetic spectrum, like X-rays and gamma rays, things that are harmful to the to humans. Light that is so energetic that it actually causes cells to break down. But in fact, it's still light. It is actually just light, very much like the light that is streaming in from my window. It is just not as, it is just, like I said, more harmful. So those two, so you can, it is appropriate to say that uh, the sun is putting out red radiation or blue radiation. Or you can say that the x-rays that you get from a hospital, they're shooting you with x-ray light rather than x-ray radiation. So generally speaking, in everyday language, radiation is used to indicate something that is harmful, light that is harmful. But again, they are the same. This basically just reiterates what I was talking about. Stars to first order, meaning approximately, radiate like black bodies. Strictly speaking, they're not black bodies. Strictly speaking, a black body is a theoretical object. There is nothing in the universe that actually is a black body. But if you squint hard enough, then stars can look like black bodies. And so that way we can use the Stefan Boltzmann law and Wien's law to determine things like temperature. So, for example, I want to know how big a star is. And I can, through just looking at how much light is coming at me, I can come up with a quantity for L, the luminosity of the star. I then look at a spectrum and look at where the brightest part of that spectrum is, and I measure the wavelength where the star is the brightest. I can use Wien's law. I can use Wien's law to tell me what the temperature is. Then I go to the Stefan Boltzmann law. I have already measured a quantity. I have already measured L from looking at simple collecting the light through a process we call photometry. And then using spectroscopy and Wien's law, I have determined T. I have determined the temperature of the object. Now I know what the surface area of the star is. And if I assume that the star is a sphere, which is again a fairly good approximation for most stars, then you now know the radius of that star. You now know how physically large it is. And that's really the game that astronomers play, as I was saying before. So, something else that a spectre is very keen on, very useful for telling us, does that mean the sun at some point has the Doppler effect as well? It does, actually. And one of the ways that we can, so last time I talked about orbits. I talked about the fact that if you're in an elliptical orbit, you can, um, you will speed up as you're closer to the sun and you will slow down as you're further away from the sun. Because all things are relative, you can think of it as the Earth is stationary and you look at the color of the sun. So when we are traveling faster, basically, let me think of that. When we are traveling faster and at an angle to the sun, we'll notice that the sun appears to redshift, or sorry, blue shift. And from that, we can actually determine an orbital speed. We can determine how fast the Earth is moving relative to the sun by looking at the Doppler effect of the sun. Again, the opposite way, if the sun is redshifted, then um, we can see how fast we're moving relative to the sun. And as I'll get into later, one of the ways that we know how the sun is structured is actually through the Doppler effect, looking at it through the Doppler effect. Because if you look at the disk of the sun, if you look at just the sun itself, you'll notice some of the gas is coming towards us. Some of the gas is coming red, is blue shifted. Some of the gas is red shifted, meaning that some of the gas is coming towards us and some of the gas is going away, and it looks like it's boiling. And so it is through spectroscopy and the Doppler effect that we're able to determine that the sun is not just the static ball of gas. Now, the thing that spectroscopy does and does very well, and really, as far as I know, is the only way that we can determine this particular quantity, is composition. How, basically, what is stuff made of? Later on, I'm going to return to this point. The universe is mostly, in terms of normal matter, the universe is around 75% hydrogen, 24% helium, and the last 1% is the rest of the periodic table. So oxygen, nitrogen, gold, extremely rare in the universe. Most of it is hydrogen and helium. Now, how do we know that? How do we know that most of the universe is composed of hydrogen, then helium, and then very little of everything else? Is we can look at the spectrum of things. When we look at the spectrum of various gases, so we isolate hydrogen in a gas tube and we make it bright, or we pass electricity through it, we make it warm. What we'll see is the emission spectrum at the top. In the visible part of the range, we will see four lines. One of them will be red, one of them will be teal, one of them will be bluish, and one of them will be violetish. And they are at very specific wavelengths. That red line, assuming you are not moving toward or away from that hydrogen gas, that red line is going to be at 656 nanometers. Doesn't matter if you measure the hydrogen gas here in Texas, in Saudi Arabia, on the moon, so long as the distance between, or the velocity, the speed between you and the gas is zero. So long as you're looking at the hydrogen at rest, then that line will always be 656 nanometers. So if we look at the sun and we see from the sun there is a line, either in the sun's case, it's actually an absorption line, but we see a line which corresponds to that wavelength, then we know that the hydrogen must be present, because if hydrogen were not there, we would not see that line. Spectra are spectral, or these spectral features, these lines, are a spectral fingerprint. No two elements will produce lines that are as numerous or or at the same locations. No other element is going to produce energy or absorb energy at 56 or 656 nanometers. Only hydrogen does. So if you can look at a spectrum and you can isolate these lines that correspond to one element, these lines that correspond to another, you can then start making measurements that, oh, the sun is made up of 75% hydrogen because I see a whole lot of hydrogen, 24% helium because I see those lines, the second one down, I see those lines in helium, and then so forth and so on. If you were to Google the spectrum of the sun, you will see that it is very complicated. There are lines upon lines upon lines. And so when spectroscopy was really starting getting out, the first thing that the biggest challenge to them, or the biggest goal rather, was simply characterizing where all of these lines were to as high a precision as possible, finding out exactly where every line in every element at every wavelength was there, so that we can do this sort of analysis in visible. We can also do this sort of analysis in the radio because these spectral features also exist in the radio for certain elements, or in gamma rays. And so for along the entire electromagnetic spectrum, spectroscopists early on were dedicated to finding and identifying the locations of all of these lines and all of these elements. It was pretty much a Herculean effort, which took decades to do. And now we're just simply refining it. So where do these lines come from? How does a piece of matter actually create these things? Oh, I need to speed things up. Um, First, we have to look at how the atom is structured. Now, typically, if you see a symbol of an atom, you're going to see something that is, someone is somewhat late. All right. When you see it, you're going to see what is known as the Bohr model of the atom. Um, this was a model that was created in around the turn of the 20th century that did a pretty good job of explaining a whole lot of effects that we see with light. And very briefly, the Bohr model of the atom is akin to a solar system where instead of the sun, you have the nucleus, and instead of planets, you have electrons. So when we look at particles, generally speaking, matter is composed of protons, neutrons, and electrons. Protons are positively charged particles, neutrons have no electric charge, and then electrons have a negative charge. Protons and neutrons will bind to each other in a nucleus. Depending on the number of protons in that nucleus, that tells you what element it is. For example, hydrogen has one proton, helium has two, lithium has three, and so forth and so on down the line. A change in the number of neutrons turns it into something known as an isotope. Not really going to get into that. It's basically the same element, just has different characteristics. And then the electron. So the number of electrons also scales with the size of the atom. A hydrogen atom only has one electron, a helium atom has two, so forth and so on. Basically, if an atom is neutral, it's going to have the same number of electrons as it does protons. In the Bohr model, the electrons orbit, go around the nucleus in perfect circles. Now, the analogy breaks down in that for a planetary system, that planet can be anywhere. For electrons, those orbits can only be at certain sizes. And that corresponds to energy, certain energy levels. Now, what does an atom actually look like? Well, we get into quantum mechanics, which is just weird. Uh, anyone who tells you that they understand quantum mechanics is either lying to you or lying to themselves. Quantum mechanics is exceedingly um, exceedingly difficult to understand, and we're still trying to puzzle it out. Question is, do we need a student ID from you for SmartWorks? Yes, you will need something known as a student set number, and I will be sending that out later today. Um, so now we look at the hydrogen atom from a quantum mechanical standpoint. Quantum mechanics has this lovely law, which has nothing to do with math, called the Heisenberg uncertainty principle. Effectively, what that says is that you cannot know the precise location and the precise speed of a elementary particle at the same time. And the more you know about the particle's position, the less you know about its speed. The more you know about its speed, the less you know about its position. Same thing has it also applies to energy and time. So what that means is that quantum mechanics doesn't deal in specifics. It deals in probabilities. So if we look at the an atom, we look at the hydrogen atom, a simple proton and a simple electron. What we notice is that we don't have an orbit. We have a cloud, a probability cloud. And what that means is that at any instance in time, if you were to look at this particular atom and were able to identify the position of the electron precisely, then it would fall somewhere in this region. The bluer the cloud, the more likely that's where you're going to find it. The the fainter or the more white the cloud is, the less bluish that it is, the less likely you're going to be finding it. First homework is going to be due February 8th. A fun thing to think about is that this probability cloud does not go to zero. You may have heard something called quantum tunneling. Quantum tunneling acts on on the premise that electrons don't move smoothly from one part to the other. You can't think of this cloud as an electron moving around a smooth path. An electron pops into existence at random places. So at one point, it's very close to the nucleus. At another point, it can be very far away from the nucleus. And the probability of its location is based on the uncertainty principle, or rather the wave function. That function does not go to zero. So it is theoretically possible for an electron that is currently in Ireland to suddenly be in my room. A piece of matter from another part of the world can be in my room and then bounce back again. Is that likely? No. It is extremely unlikely. It probably will never happen within the age of the universe, but it is possible, which I think is just amazing. All right, anyway, let me speed this up. So how do, yeah, all right. Let me talk about how those lines come into existence. Nature is lazy. The electron is going to be in the lowest orbit possible. So let's return to the Bohr model of the atom because it's simpler to think about. The orbit that is closest to the nucleus, the electron has the least amount of energy. The larger the orbit, the more energy that the electron currently possesses. Nature is lazy. That electron wants to be on the couch. It wants to be as small, as close to the nucleus as it possibly can. So when a piece of energy comes at it, when a photon hits that electron or hits that atom, and that photon has just enough energy, a very specific amount of energy, then the photon is going to move from its location to a higher energy level, to a higher shell. And then, because it wants to be on the couch, it's going to very quickly fall back down again. Unless there's another photon behind it, basically hitting it again and hitting it constantly, that thing is going to fall back down. That electron's going to fall back down, and that energy that it absorbed, that caused it to move, is going to be re-emitted in a random location. So, and the where the electron is to where initially to where it is where it ends up when after it gets hit by a photon, that is a very discrete amount of energy. And if you remember, photons carry a discrete amount of energy which is equal to its wavelength times its frequency. So that red line that I was talking about, 656 nanometers, that corresponds to a very specific energy and a very specific type of photon which interacted with a hydrogen atom that caused that electron to move in one way or another. So let me end this. And there are slides related to the Doppler effect, which I probably won't be able to get into. So definitely check that out. But let's go back to the three types of spectrum. A continuous spectrum. Now we have this very hot source, very white light source that is putting out energy, is putting out photons in all directions, basically across a smooth range of wavelengths, your blackbody curve. Now let's take some of the photons and have them pass through a gas cloud of hydrogen. Hydrogen atoms, if the most of the energy, most of those photons are going to hit that or hit the hydrogen atom and just pass right through it. The hydrogen atom isn't even going to notice that they're there. But if one of those photons corresponds to an energy which has a wavelength of 656 nanometers, then it's going to interact with that hydrogen atom. It's going to get absorbed, and so now that photon, which would have normally come and hit your eye, is now gone. But very quickly, that light, because energy cannot be created nor destroyed, that light gets redirected in a different way. So if you are looking through the cloud, because the light has gone away, you see a dark line. You no longer see light at the 656 nanometer range. But if you're just looking at the cloud, then some of that light that got redirected will get redirected in your direction. And so you will see light you will see a bright line at 656 nanometers. Again, at most all other wavelengths, the hydrogen atom is going to ignore those photons. So they're going to pass through the cloud, and you're only going to see that light if you are in the line of sight of the object through the cloud. So everything else is going to be bright. If you're looking at it at an angle, then you're not, a lot of it is just going to be dark. You're only going to get those photons that have been redirected.